So I'd like to now state a few important properties of projection matrices. Projection matrices are pretty interesting. So the first two properties are the symmetric and idempotent properties. We've already seen the adjective symmetric. Symmetry means that the transpose is equal to itself. So it turns out that every projection matrix is symmetric. The transpose of a projection matrix equals itself. Our new adjective here is this adjective idempotent. To say that a matrix is idempotent is to say that the square of that matrix equals itself. So every projection matrix is idempotent, meaning that the square of that projection matrix equals itself. I like to think about this idempotent property geometrically. What does it mean for the square of a projection matrix to equal itself? Ultimately, what this is saying is that if we project a vector onto a space, and then we try to project again, we won't change the projection. So there's never any need to project a vector twice. Once we project once, we're fixed in the space. Why are projection matrices useful? Well, for us, one of the reasons they're useful is that they offer a classification of vectors. To say that a vector v is in the space you care about is to say that when you project the vector, you don't change it. So if the vector v is already in the space you're trying to project onto, when you project, you don't change the vector at all. On the other hand, let's say that v belonged to the orthogonal complement of our space. What that turns out to mean is that when we project, we produce the zero vector. So if we want to test whether or not a vector is in the orthogonal complement of our space V, we can multiply by the projection matrix and check if we get 0. And another thing that projection matrices have, which I think is interesting, is they're dimension conscious. This is just a silly way for me to put words to a famous formula, which is the formula that says that the trace of a projection matrix is always equal to the dimension of the space we're projecting to. Remember, the trace of a matrix is the sum of all of the diagonal entries. So let's look at an example here. Here, I'm looking at an example where I have some matrix A that I was studying, and I was interested in the column space of A, and I went ahead and calculated the projection matrix onto the column space of this A. So here we're looking at a projection matrix. Let's start thinking about the properties we just listed. One thing I could do is I could look at the trace property. I could sum all of these diagonal entries to look at the trace of this projection matrix. So that's 6/7 plus 6/7 plus 6/7 plus 3/7. So what is that? That's 21 over 7, which is 3. And remember, our dimension conscious formula tells us that the trace of a projection matrix is the dimension of the space we care about. So I now know that the dimension of the column space of this matrix is equal to 3. And another thing to remind yourself is that's the same thing as the rank of the matrix. So by somebody giving me this data, one thing I can infer by looking at the trace of the projection matrix is that the rank of the matrix I'm studying is 3. And remember, one of the useful things about projection matrices is that we can use them to test whether or not a particular vector is in the space that we're projecting to. This matrix, this projection matrix, projects onto the column space of A. So I have two formulas here. On the left, I'm taking that projection matrix and I'm multiplying by the vector -1, 6, 5, -6. Well, when I multiply by -1, 6, 5, -6, I produce the vector -1, 6, 5, 6. So if I call that vector v1, what I'm noticing here is that p times v1 equals v1. On the other hand, over here, I'm taking that same projection matrix, and I'm multiplying by another vector, v2, whose coordinates are 4, -7, -5, 1. And when I do the multiplication here, I produce the vector 2, -5, -3, 5. So evidently, the projection matrix multiplied by v2 here is not equal to v2. This actually tells me something. What it tells me, because P times V1 is V1, is that V1 is in the space I care about here, which is the column space of A. And since P times V2 is not equal to V2, that tells me that V2 is not in the column space of A. So here I'm using the projection matrix to test whether or not vectors are in or not in the space I care about, which here is the column space of A. What are some other properties of projection matrices? Well, if we think about the formulas we stated previously, we said that if a vector is in the space we care about, then P times that vector equals that vector, which is the same thing as P times that vector equals 1 times that vector. On the other hand, if a vector is in the orthogonal complement, then P times that vector is equal to the 0 vector, which is the same thing as P times the vector equals 0 times the vector. All of this comes together in a statement about the eigenvalues of any projection matrix. So it turns out that the eigenvalues of any projection matrix are equal to 1 and 0, and the justifications are exactly the equations that we just stated. The eigenspace of a projection matrix with the eigenvalue 1 is equal to the space that we're projecting on. And then on the other hand, the eigenspace of the projection matrix with the eigenvalue 0 here is equal to the orthogonal complement of the space that we're interested in. Consequently, we can say something about the geometric multiplicities of these eigenvalues. The geometric multiplicity of 1 as an eigenvalue of a projection matrix is equal to, remember, this is the dimension of the eigenspace, which would be the dimension of the space V that we're studying here. The geometric multiplicity of 0 as an eigenvalue would be the dimension of the orthogonal complement, which would be n minus the dimension of the space we care about.